It's my pleasure to introduce our next speaker, Dr. Klaus Schuegraf, and he's currently CTO of Silicon Systems Group at Applied Materials. And Klaus was a graduate student here at Berkeley with Chenming, and he graduated in 1994 with his PhD. And currently he's the vice president and CTO again for the Silicon System Groups at Applied Materials. So with that, let's welcome our next speaker.
Thank you, Ali. So before I start, a little bit on the philosophy before we go. We're here, of course, not to talk about what does it say, electrons to electronics. You know, I was sitting in the back with Elise. I was going to weave in a new interest that's developing of mine. It was going to say electrons to elections. But I see Elise has that covered, so I can strike that subtitle. When I reflect on today, I spent my whole morning in Berkeley. I arrived here at like 6 o'clock in the morning and decided to go to the gym downtown, work out. So the nice thing about being in Berkeley and working out for a couple hours before you actually have to take a shower and get ready to come up here and climb up the hill like you did as a student, where I remembered it was exactly 17 minutes to walk from my apartment to Corey Hall and make class. So I remember that on the way here. But really reflecting on the philosophy of why we're here to celebrate life. And of course, we're here to celebrate Chenming's life and our part in it as a family. And that's very clear. And of course, what is life if it's not the people that have made it special for all of us? So really like to thank Chenming. I want to, in the spirit of some philosophy and what I learned at Berkeley that had nothing to do with the stuff that I find useful into day-to-day commerce, is number one is creativity. Chenming is very interesting. So I found Chenming's class, device physics class, I took in my first semester here. I started off semester in the spring. It's typical for me to always do something a little bit odd and off kilter. And starting in the spring was one of those events. So, it was very interesting. Chenming's like, be creative. I'm like, there's a professor in electrical engineering telling us to be creative. I go, oh, this Berkeley place is sounding more interesting already. And what was inspirational was we were really transcending the mathematics to think about the device physics and just physics and problems in general at a much more intuitive level. And I found that incredibly inspirational. And it's actually become, I'd say, it was always there in me as an individual, but as really what happened through those years in PhD study world is the next thing that happened is not only was it an appeal to creativity, but it was a question is there's so much complexity, right? If you actually take a look at a device, Clement showed the pictures of the three-dimensional device with subsurface leakage and all that. Our first term paper, I think, in that device physics class was about dealing with the sub-threshold leakage currents, working on the Toyabe paper and stuff like that. Fun problem, very mathematical, but there were simplifying assumptions to actually allow you to work through it in a closed form and analytical perspective. And what is truly the gift of Chenming is to break down the complexity of enormously difficult problems and to render them in a simple format. And I think we have all learned how to do that. And I use that in my daily life more than anything else, is how to take something very complicated into something simple. And I know for me personally, that's what drew me to Chenming. I know for a fact, because I always want to bring it down to what is the essence? What are the top 2 or 3 things? What really matters here, right? And so, there was resonance there. And then the other thing that was very interesting, and this perhaps came later, is I was talking to Chenming when he had just arrived at TSMC as a CTO, and we had a discussion, and I was sort of curious. I go, so what brings this about? It's a little bit different, right? And Chenming's telling me a story about how he was out in the mountains climbing Everest, which I thought was interesting because I didn't even know he climbed, right? And so you get this idea of climbing ever higher peaks, pursuing your dreams. And what could that be other than pursuing Moore's law or making regular change happen? But more importantly than that, inspiring the confidence in each of us to be able to do that and feel comfortable doing that in a world that has tremendous amounts of complexity, and being willing to attack that on a two-year cadence, right? And then what I really see in that is courage, right? I mean, courage. Quite honestly, all of us doing this device physics and stuff like that, we're very well trained. We're very proficient at all that. But at a life lesson, what's much more valuable for all of us that I see is, I look at Ramuni, and Ramuni and I were trading emails in the last couple of days. And she sent me the link to her music last night, right? And I was like, wow, that's incredible. It's really cool. So I was listening to this last night in my bedroom, and I was like, this is pretty cool. But when Ramuni's on stage here singing to us, and it was fantastic, I'm like, she is able to muster the courage to get in front of a bunch of us, who some of us know are better than others, and she was able to sing from her heart and her soul. And that is truly phenomenal, right? And again, I think the idea of creativity, the complexity to get to simplicity, the courage, the confidence, this is what we really learned at Berkeley. The science was fun. The leadership around the science is fantastic. We all have wonderful careers. It's very interesting. I spend a fair amount of my time, particularly in the first half of the year, every year, traveling globally, visiting all the different top customer sites around the world. And literally, I can't go to a customer without seeing one of Chenming's former students. Because they're all in the leadership positions at every single company, right? Whether it's TSMC, Samsung, UMC, wherever. So I feel like I'm always at an alumni reunion event whenever I go travel the world. So which brings me to what do I do? And so the first question you might ask is, why the heck does Applied Materials have a device physicist running its technology function? The answer to that is because I like making wafers, actually. No. that picture, by the way, was presented to me when I was here in March. I gave a talk that the title of this talk came from that presentation. It's online. This talk is a different talk. I just choose the title. I chose the title in that picture because, it's very interesting. So, when I really think about the 2 or 3 people who have been most impactful in defining me as a human, as an adult, is my dad, who was a fairly tough disciplinarian and taskmaster. His background is a physicist, and he was a crystal grower. So his big thing in the 50s, when he was getting his PhD in post-war Germany, was he was trying to grow silicon crystals. So that's what he used to do for life. And then eventually he moved on and did things in CVD arena and things like that. And he was fairly accomplished in this and always very rigorous, wanted to make sure everything was perfectly. You had to understand your science and all this other stuff, making equipment. And I was like, the first couple jobs I had after high school in the summer, he's like, yeah, no, you're not taking one of those engineering jobs. You're working on the factory floor because you need to learn what an honest day's work was. I mean, this is my dad. So I was out there boring through stainless steel with a drill and things like that. That's how we make equipment. And I was convinced I would never have anything to do with semiconductors in my life. I was like, this is plumbing. It's fancy plumbing, right? So I was like, this is not what I want to do with my life, right? And then, of course, I was thinking, I'm going to work on, systems and some maybe IC design or something like that. And then I ran into Chenming here at Berkeley, and I was like, okay, that's pretty inspirational. I'd actually like to go do that. It's somewhat related to physics. I haven't gone completely to the dark side, right? And then sure enough, when I was done with Berkeley, I went up to Micron. And I met the person who I actually work for today at Applied. And he was visionary in his own way. And his view of the world was single wafer manufacturing is the way of the future. This is how we're going to make transistors one day. And I walk in the fab, and I look at our run card, and it's like, I saw maybe one single wafer process that was not an etcher in our entire process flow, and that was an RTP step. And of course, he was the person responsible for the RTP section up at Micron. And yet, we got working on this stuff, and we started envisioning what would the world be like if you made transistors with single wafer process equipment. And we wrote some very high-level, vague papers in the mid-1990s together. And what we learned was a few things is, well, the single wafer stuff is great because you can do experiments very efficient. Every single wafer is its own experiment. You can't do that with furnaces and batch processing. And so what we realized is learning and the rate that you learn through developing a process is much more important than actually doing things the lowest cost way. And at Micron, we were considered heretics because it's all about cost in the memory business. So those are three people who have a tremendous amount of impact in my life. And it partially gets at why there's resonance with someone who's a device physicist working in applied materials, trying to define what are the interesting materials and pathways that we can work on to drive Moore's law forward. Okay. So now that I've got that intro, long-winded intro, the key themes in the world today, of course, we've heard all about this today. Mobility is driving the technology landscape, the market as well. I'll get into that. Cost is becoming the big challenge, and cost renders its ugly head in all sorts of ways. And these become our problems. As engineers, cost becomes our problem. I mean, it's great to say, that's really a finance problem. The reality is, when you start thinking about products, whether it's the products that we make, which is equipment for manufacturing semiconductors, the products that a foundry makes, which is the wafer, or the end product, which winds its way into an electronic system, cost is something that we all have to worry about as engineers. And then the other thing we see is that there's a tremendous increase in the complexity. You start looking at the FinFET or the 3D, the gate all-around structures, the stuff Ali was showing us with these two-dimensional devices. Those new architectures are very complicated. They rely on new films, and they rely on patterning technologies. At IDM, I had the misfortune of running into the press, and I hadn't fully thought through what I was saying when I said it. And I very boldly said, there's only two problems in the industry today. Everybody's working on FinFETs, and everybody's worrying about EUV. And I'm afraid that's going to be in print next week. I wish I had not said that, but it is true. I say it here because it really is part of the focus is very important, and the technology and economics is driving this. So one thing, if you're on the memory side, Conquer, I apologize. I'm going to talk more about logic today because it's not that some of this is not true for the memory side, particularly when you look at the 3D architectures that are going on in the NAND side. The device problems are all the same. The question is, who's driving the investment and who's driving the product development for equipment? It's all on the logic side. And increasingly, the technology driver for the roadmap is coming from logic, and memory has to adapt and use what gets developed for the logic side. So this is the backdrop. Of course, several of you have said this. Even Ramuni gave the very a real-life example of this. I was able to record myself in a basement downstairs, right? Transistors are so cheap. The power is so good. We take these incredible phones everywhere we want. We call this the mobility area. That's the backdrop. And of course, how long can this go on? 20 years ago, we were sitting here. It wasn't clear how long it's going to go on. I'm pretty sure this next 10 years looks good. Clement said the same thing. The devices look possible for the next 10 years. It's the 10 years after that. That's a lot more interesting of a problem. What's that world look like? Ali gave us some good insights on that. There's more stuff coming. It's either going to be 3D in a vertical sense or 3D in a horizontal sense, right? And it's fairly clear that's coming. And the question is, how are we going to go do all that? And that leads me to the cost challenge. So I know many of you are in the audience, and I didn't want to offend anyone who is a customer or of ours or a competitor or whatnot. So what I've decided is if your company names are shown here, they're ranked by market capitalization, which is actually a pretty good way to do a cost challenge chart, right? So let me explain it this way. The biggest problem that we face today is just the sheer capital intensity to build a fab. We're starting to see fabs, productive fab is on the order of a $10 billion investment. That's fairly significant. The die cost on a cent per square millimeter basis is going up for logic technology, and the R&D cost, due to the complexity of what people are looking at with these 3D architectures, the many types of new materials that are created to actually make well-performing devices, this is going through the roof. And so the question is, well, who's going to pay for all of that? And you can look at that in two perspectives. You can look at it in the quadrant in the upper right. You can look at it in the quadrant of the lower left. But let's start with the end users, because this is a tectonic shift in the landscape. There are new business models emerging. You have fully vertically integrated providers of technology to consumers. This is completely different than desktop computing or the microcomputers or the mainframe computers that came before it. Led by Apple, there's Google with the Android, Amazon with the e-commerce site and the tablet and the cloud. But what we're seeing is a tremendous growth and creativity in new business models. If you had asked even 10 years ago and said, well, what's the best way to provision hardware or microelectronics to people, I'm not sure we would have said it's a fully subsidized tablet that you can get for $149, and the thing is amazing. My 2-year-old plays with his Android, with his Kindle Fire, and the stuff he's got on there, I couldn't have dreamed of it when I was a kid, and he's learning at a rate that it's just unfathomable, the types of things he asks. So we can talk about that later tonight. It's just it's a very interesting perspective. So we have to realize that technology is touching all of us when we start talking about deployment in our hands in a mobile form factor. And then on top of that, each one of these companies is getting paid different ways, and they have very deep profit pools because they're starting to reach $6 to 7 billion global consumers. And no amount of technology company has been able to address that many customers in the past. And then you make it look simple. So let's take a look at the guys who actually make ICs. And the top three here are Samsung, Intel, and TSMC. And what's going on here is certainly it drives our business. These three customers on their own are driving on the order of 60 to 75% of our business in a given year. And that's an incredible amount of concentration. These are the market leaders. They're driving incredible volumes. They get economies of scale that make it all possible. But even they are struggling with the cost of R&D and the cost of these factories, which is leading to more concentration. It's a feedback loop here. On the supplier side, there is consolidation. There's active consolidation. I can go through every single one of these companies. ASML has just acquired Cymer in a very high-value transaction. Applied Materials has engaged in a few acquisitions. And what you start seeing is what used to be a very broad, diverse set of suppliers into these three handful of major manufacturers is becoming, it really is going to become 5 or less. And then the question is, there's a lot of different R&D paths. And what happened in the old days is you saw a roadmap like I'm about to show, and you say, or what we've heard about this morning, FinFET, and then when you talk about moly sulfide and all this other stuff, and you go, well, every single company would try one path on their own, right? But when you start getting to only 5 viable players who each have their own speciality, it gets very difficult. How do you get certainty around a solution path when there's so many different ways to go? Because companies are only willing to invest a certain amount and place a certain amount of bets and things like that. And that is the cost challenge. And how we transcend that is really what we have to do going forward to be able to drive this type of roadmap. This roadmap is naive. I learned that here too. It is better to oversimplify a problem and then you can throw stones at it than it is to have a complicated problem that everyone will throw stones at anyway. So it is oversimplified. But just to give a perspective, what I have here is sort of on the aggressive end, perhaps where is the industry leading technology node, what is the interconnect CD, abstracted a little bit, but you can actually predict this stuff. And it's very interesting. I talked to a friend of mine at Intel yesterday or 2 days ago at IDM. I was like working on 10 nanometer, and I said, yeah, in 4 years from now, you'll be working on 5 nanometer. I was like, exactly. So now you can just imagine, you do that a couple more times. Let's go back 20 years, right? 1992, you're running a 350 nanometer, 0.35 micron process. 20 years later, that's 2 to the 5, 32. We're working on 10, 14 nanometer. It's clockwork, right? It's unbelievable. Can you imagine something, you're working on technology that's predictable? But everything underneath it is changing all the time. Okay. So one thing that's happening to go deal with cost cost challenges, there's wafer scaling. Hearing a lot about 450 millimeter and stuff like that. There's good and bad with 450 millimeter. It's potential. The cleanest way to look at 450, and I'm not talking about applied strategy here because it's not actually great for applied strategy, but what is great for the world at large that uses semiconductors is going to reduce the cost of computing and mobile computing to unprecedented levels, which means the demand will be even greater than it has ever been before. Transistors, we went to IDM. All we heard about was FinFET and ST talking about FDSOI. Nothing disparaging about Thomas Skutnicki and the ST guys, but it is FinFET. I'll give another funny story. I was in a session yesterday morning. It was on germanium transistors. There were 7 papers in the session. One of them was presented by TSMC. 3, Chenming was an author on. They were all from Taiwanese universities. And then the other 3 were from a collection of European and Japanese research institutes. But so here we are, we're talking about the thing after the FinFET, and Chenming's already got his hands all over that one. Actually, let me say that a little bit differently, and probably more realistically, is that what we're also seeing with concentration and consolidation on a global scale is increasingly the manufacturers, particularly TSMC and Samsung, are realizing that they need to grow their own talent locally. And the only way to do that is predict where you're going to go and nurture the university environment in your local space to make sure you get the talent so you have the feed in to be able to solve these problems. Because the complexity problem can only be solved with trained and talented engineers. And so what we're really seeing is that many the larger manufacturers in their own backyard are starting to take a serious investment into the personnel they need to staff their R&D efforts, right? And that's the 2 elections piece that is actually becoming an extremely interesting part of the semiconductor roadmap. On the interconnect side, it's coming along. Dual damascenes keeps going, but it's fairly clear when you start taking a look at these architectures that the wires are actually a pretty ugly problem going forward. And this is going to be a major problem, maybe not to the 10 nanometer node, but certainly beyond. When you start taking a look at wires where the dimensions are 15 nanometer wire dimension or 10 nanometer, these things are not really good conductors anymore. Just the insulators and the cladding you put around them, they wind up severely impacting the net wire resistance, and that can be fundamental. Of course, there's some design tricks and ways to get around it and deal with it. We had a very interesting forum at the IDM a couple days ago where we had different discussion on alternatives and approaches to deal with it from a design perspective. But when we, like for instance, Professor Javi was talking about all the different semiconductor grade materials that you can use to enable new types of devices, on the flip side, we have the exact same problem. You've got the exact same problem, and how do you engineer the interconnects? Is it copper-based? Is it some other new wonder material? And there's a lot more sort of interest in the quantum effects of transistors at these dimensions than there is in wires at those dimensions. And they're both very fundamental problems. On embedded memory, people are looking at MRAM, always will be. And the biggest problem, of course, is that of patterning, which is why I say that EUV is probably the biggest issue. And largely, it is not because there is no other way to do it. You can do these multi-patterning schemes. You can use multi-patterning schemes, immersion multiple times, like Conker was talking about this morning, and be able to make sub 20 nanometer gratings. It's no problem. The question is, can you do it for a logic process on the feature sizes you need at a cost-effective and yield-effective approach once you get some random dimension as you get in the logic layouts. So there's a question that comes in through patterning, which is technical feasibility versus cost feasibility. And that's probably why the other half of the problem that everybody's really worried about today is not just how do you make FinFETs and then make FinFETs go scale a few more nodes, but also how do you pattern them in general, and that's where EUV comes in. So let me talk a little bit about my view of the world of advanced transistor, which doesn't look all that different from Clement's view of the world, although it's more cartoonish because we don't actually make the stuff. And most of the stuff that we do process that is customer related, we will never show anybody. That's part of a IP protection strategy. But what we absolutely see is the day of that good old planar CMOS transistor that we all learned to love in graduate school 20 years ago is gone. Of course, the guys who were here 10 years ago or so, they came up with this clever idea called the FinFET, which is now in production. And Clement, you were understated when you started your talk this morning. You did mention the 1996 paper, but I have a completely different view of the 1996 paper. My view of the 1996 paper is that was the background study to get the ARPA funding to go actually do the FinFET program. That's my personal opinion, but again, I think you understated. Again, so many bright and creative people in the room, and really the work is built on the giants that went before. The 3.5 FinFET or the germanium FinFET, it's an incredibly interesting problem. It's real. And when the first time so this gets a little bit at why does Applied Materials care about to have a device physicist working at it. It's very interesting. About 2 years ago, we were having, 3 years ago, we had this and this was before Intel announced that they were doing the FinFET. We had this very intense internal debate. Should we be working more on the conformal types of process and materials that are necessary for a FinFET? And pretty much most of the business leaders, or the product GMs were saying, FinFET's not going to happen before 14 nanometer, if then. It's just too complicated. And then I pulled out my electrostatics trump card. I was like, it's very simple. It's all about electrostatics. I just played one card. Again, keep it very simple. I said, can you really afford to take that chance, right? Of course, 6 months later, Intel said we're going to FinFET. And of course, at that point, we're reactive just like everybody else. Said, we need to make sure we have a good roadmap all around the FinFET and its extendability forward. Same sort of thing is happening when we have germanium or 3.5 materials. The reason that conversation was important is when you start taking a look at what happens when you go to a new fin material, it gets very simple stuff. It's just, what's dielectric constant germanium? It's almost 16, around 16. Well, that's more than silicon. So you're guaranteed, once you go to a fin, you're going to stay there forever. Every other material you want to look at has electric constant, dielectric constant, which means the electrostatics are a nightmare. We take a look at a device like this, it's all about interfaces. So increasingly it's becoming, there's materials aspects of making the FinFET happen, conformal everything, conformal materials that have to be as good as PVD type materials. The interfaces need to get managed. These are all the ugly problems you're dealing with, Clement, on a daily basis, I'm sure. But it gets more interesting when you scale it. It gets even more interesting when you scale it. Whether you scale the material going to germanium or something like that, or scale it to further dimensions, we'll come to that. The FinFET is an extremely interesting device. And then maybe out there in the dream, there's this concept of the nanowire. And it could be either in a two-dimensional, in a vertical or in a horizontal configuration. I show it here intentionally in a horizontal configuration because that's the sort of thing that university type research is great at, right? Is figuring out what would that world look like? Because if you want to make transistors that look like that, it requires new types of processes to be able to connect sources and drains, new design styles, new EDA capabilities, new modeling capabilities. It's extremely fertile ground for what-if scenarios for research. And that's why I leave it out there. Now, sure enough, we had this great idea. So this is, again, thinking ahead. And sure enough, within 6 months of just throwing it out there, we see some of our customers actually in the advanced research stuff publishing stuff on this. So it's maybe we got this one wrong, but it's on the far end out there. Okay, so then we talk about the FinFET. So the FinFET's easy, right? We've all seen Intel's wonderful pictures. They call it the Tri-Gate for some reason. You have to get in some very interesting ledger domain to figure out why it's not a FinFET, but that's a different story. But when we take a look at scaling the FinFET, you realize one of the big problems with the FinFET is the parasitics are outrageous, just because the gate to drain overlap is going to become a major problem. Not only that is everything's gotten smaller, these fins, so let's just say gate length is on the order of 15 nanometers, just to pick a number. That means your fins are going to be on the order of 8 nanometers, and now you need to make point contacts to be able to route wires in and out, so the contact resistance becomes the major issue. And all that at the same time, if you have to be able to make 8 nanometer freestanding structures that don't fall over. And anybody who's working on the leading edge in structures that are freestanding, less than 20 nanometer geometry, knows that wet cleans and those structures do not behave well. The capillary action in these wet processes is just is overwhelming and causes them to collapse. The other thing is you can't have any oxidation of any of the silicon or other new materials, so you need to protect them, which adds to more complexity. So again, conformal protection, how to keep them, how to keep these structures from eroding just during the processing, and that's just the basics of how to make a fin and preserve it. And then we haven't even gotten into all the fun part of the device, which is where the action occurs, which is nowadays in the gate stack with the gate interface getting EOT scaling, a topic near and dear to my heart. The metal gates, both N and P type work functions, can't do it by implant anymore. And then when you take a look at structures like this, what's really interesting is 15 nanometer gate length. There's not a lot of room in here, so you need pretty good new types of materials. That the usual materials you can use here is they don't actually have the same properties as bulk materials, and not only that, they don't have the same properties when you put them in a trench as they do on a planar structure, which is leading to quite a bit of innovation for how do you get band edge type materials so you can get good device performance at the same time as good resistivity. And not even shown on any of this is how do you do a self-aligned contact, which is how do you make all this stuff fit together. The more interesting problems are so something we're playing around with at a concept level is the films and materials that you can minimize. So people are using these stressors, so you can envision a stressor here that has a lot of contact capacitance between gate and drain. And that really defeats the purpose of scaling, which is to improve the performance. So we're playing around with all sorts of neat ideas on how can you shape these structures so that you can get the strain, and at the same time minimize the capacitance. And you say, well, why would you want to do that? And the question is, it requires a fair amount of ideas on what types of K values you need, what types of gap filling properties you need in the materials, what are the thermal compatibilities of the materials for the processing, and that's all very interesting stuff, right? And all of this is new materials that don't exist. You can't go read a textbook on semiconductor processing. You actually have to invent the stuff, which means that there's a lot of drive for chemistries as well as some direction of those are interesting materials to go look at, right? And then similarly on the contact, how do you make good contact resistance? Interesting problem. So we're looking at that from all different perspectives. And increasingly what we're finding at the major conferences, we're seeing that a lot of our customers don't like to publish stuff, particularly the nitty-gritty details of how stuff works and what the electrical performance does. I see a lot of you saying, yeah, those conferences are getting a little boring. So what we've tried to do is come up with sort of a, again, simple, a canonical framework that we can use to go say, here's how we want to go evaluate a subcomponent to this. And what we tried to do is before we take that too far along with customers on some of it, or we take some of our interesting ideas that didn't quite work out and we publish it, just to get some dialogue going in the technical community. So that's the sort of framework that we have in our technical program. So this I can skip. Anyone, we know all about high K. The interconnect is a similar interesting issue, just at a high level. Is if you talk to most of the fabless community, is they're beginning to scream about RC delay. It's gone from what used to be a linear curve to an exponential curve of rise. What this band is, it's essentially the range you could expect with modest perturbations of the dimensions and the materials that are used in the Damascene processing according to the ITRS roadmap. So we looked at this, and essentially all this is we had one of our young engineers put this in SPICE, model it up, make a transmission delay line model on narrow dimensions. So agreed, it's a canonical example. And then we said, well, how would you approve it, right? And then what we did is we said, let's go pull out all the stops. What are all the things you can do? Barriers, materials. And we came up with a list of like 12 or 13 things that we could do, invent new processes and materials to go make that happen. And so we started showing that to some of our customers, and they said, well, that's very interesting. The first time they said, oh, you're crazy. This was a few years back still, and it was like, who's thinking about this, right? And well, what started happening is slowly we showed the list of here that what we're starting to see is everything we put on the list got pulled by customers at different times, right? So this maybe answers some of the questions. Well, I know a lot of you asked me, what the heck is a device guy doing at Applied Materials? But and I'm not an interconnect guy, but I've learned more about interconnects at Applied Materials than I ever knew anywhere else. It's absolutely fascinating science. This metal science is absolutely just phenomenal. And then this is my slide to prove that I'm still an engineer. I can still make PowerPoint slides like I'm at a conference. These are the areas that we're really working on, and this is the fundamentals, the technologies that drives the outputs. When we take a look at scaling to 450 or driving the new types of processes in the world, the reason companies like Applied Materials became so successful is that we're largely built on a plasma processing base. And the reason plasma is so interesting, it was a way to drive reactions forward at a low processing temperature so that you could actually make semiconductors, and that not everything got done at high temperatures like in furnaces. And what we're seeing is that as you start talking about these new types of dielectrics and these new types of films and the shallow junctions and whatever else in these process, the interfaces, they don't do well with temperature. They really don't do well with temperature. You know, the melting point of germanium is a good 500 degrees Celsius less than silicon. So that sort of compresses your processing window. And so what we're looking at is, particularly when we go to 450, we're looking at new energy sources to drive processes, which is a pretty interesting cross-fertilization of materials science, electrical engineering, physics, and physics in different perspectives. It's not just the RF side, but also from light. There's a lot more use of light and optics and optical processing in these exploratory ideas. The chemical delivery systems to be able to make to deliver all the different precursors that are not the simple stuff like silane and chlorides to halogen-based films. Now everything's organometallic. So you need like forget the PhD in organometallic, in organic chemistry. You need to, which organic chemistry was an interesting thing. Didn't want to really do that because I thought it was too much memorization. Now I realize that was a major failure in the educational gaps because I could have probably spent a little bit more time learning about organic chemistry, and that would have been very. But the range of vapor pressures that you have to deal with, the liquid precursors, solid precursors, as well as gas precursors, and how do you deliver them with the different vapor pressures? Coming up with, again, this is the idea, is if you take a look at each one individually, it'll cost you a fortune to go develop a solution for each. So you need to come up with canonical, this is a range of things that you want to look at, and then how do you get a solution for that, right? And that's getting at maybe one of the question on the materials, how do you get screening methods, right? How do you get a solution that is more cost effective, more productive, stuff engineers are very good at, when they take a step back, and that's what university is excellent at, and thinking about what is the real problem here, rather than just having engineers who we graduate and they just can solve a linear problem. Said, go solve this. It's take a step back and solve it more fundamentally. If we take a look at the FinFET, it's the same thing, right? You could keep making planar transistors till the end of time. The question is it worth making those transistors till the end of time? So this is where engineers come in: is do something different. And then, of course, the work here at E3S with the 100 millivolt switches and the high packing density logic, that stuff's absolutely groundbreaking in the future. And of course, EUV is such a big problem that it goes without saying that there's a tremendous amount of effort in the industry going into this. And so I'll close on a couple things, but if you take a look at where the best people are going in the industry today, They've always been going to the hardest problems. The hardest problems, of course, are FinFETs and EUV right now, but cost is quickly becoming one of them. And so getting a full grasp on what is the cost and what are the trade-offs in being able to solve that, that is the major issue going forward. And to think about how to do that, the last word here is that of collaboration, which is we're increasingly trying to stress that, understanding that there's only three real manufacturers at scale in the world driving these extremely complex processes. And then the question is, everybody wants their own solution, so you have to find a way to collaborate with them and protect them from learning from each other without them wanting to. And so that's a key thing. So we've got complexity, concentration, and collaboration, but remember the more important ones are to celebrate, to have creativity, to have the courage, and just have the confidence to go keep innovating. I think that's the story here. Okay, thank you.
Klaus. You know, I want to give a short clarification. It's probably unnecessary. Klaus' title at Applied is VP and Chief Technology Officer of Silicon Systems Group. I want to clarify the Silicon Systems Group is 80% of Applied Materials. So Klaus is the chief technology honcho of Applied, of the world's second largest semiconductor equipment company. I don't know if you were here, Klaus. Did you hear Sujay's introduction or opening remarks? All right, so I was surprised. I thought, the paper that I co-authored that had most citation would be something about FinFET, but at least it's not. Not only Klaus was brilliant as a researcher, he also has drive and take initiatives. He actually took the lead to say to me that, hey, we should write a book on oxide reliability, something that was started, Steve Holland, Yixin Chen, and then Elise and others have developed, and Klaus then culminated into really the modern ultra-thin oxide reliability. And he actually wrote 2 chapters and put on my desk. And I dropped the ball and didn't get that project finished, so sorry about that. But you. All right, yeah, let's get it going.
At the mercy of boring you with the story of how I'm a bad student.
All right, you use this.
I
promised to Chenming when I went to Micron, because I sort of pushed, like usual. For those of you who know me well, I'm a little bit pushy. And I was a lot more pushy when I was younger. And I was pushing to go out and get a real-world job. So I promised to Chenming that I would finish the book if he would let me leave. And it'll break your heart, Chenming. I actually wrote 10 chapters of the book. I had a draft for 10 chapters of the book. I threw it out 2 years ago when I cleaned out my garage.
You remember Richard Newton. He wrote a book, an EDA book. We all expect that to be really groundbreaking. And then his house in Orinda burned, and that copy burned. Can you believe he did not have electronic copy? But that was many years ago. So.